Imagine a robot navigating a maze. At each position, it can move up, down, left, or right. Some paths lead to the exit and earn a reward of 10 points. Others lead to dead ends with 0 reward. The robot doesn't have a map. It must learn through trial and error which actions work best in each location. This is the challenge that Q-learning solves. The algorithm learns a value for every state-action pair. Q of state S and action A represents the expected total reward from taking action A in state S and then continuing optimally. After enough exploration, the robot builds a complete table. At position 3,2, moving right gives a Q value of 8.5, while moving left gives only 2.1. The robot simply picks the highest Q value at each step. The Q function maps each state action pair to a number representing its long-term value. Think of it as a lookup table. For every possible situation and every possible action, we store an estimate of how good that choice is. The optimal Q function satisfies a fundamental relationship. The value of taking action A in state S equals the immediate reward R you receive, plus the discounted value of the best action you can take in the next state S prime. The discount factor gamma controls how much we care about future rewards versus immediate rewards. When gamma equals 0.9, a reward 10 steps ahead is worth only 35% of its face value. This relationship is called the Bellman optimality equation. If we knew the optimal Q values everywhere, we could act perfectly by always choosing the action with the highest Q value. But we don't know these values initially. Q-learning discovers them through experience. Q-learning updates the estimates every time the agent takes an action. Start in state S, take action A, observe reward R, and arrive in new state S prime. We now have real data, the actual reward received, plus an estimate of future value based on the best action available in S prime. The temporal difference error measures how wrong our current estimate is. We predicted Q of S, A, but the actual outcome was reward R plus gamma times the maximum Q value in the next state. The difference between these is the error. The update rule adjusts our estimate toward the observed outcome. We take our old Q of S, A, and add alpha times the temporal difference error. The learning rate alpha controls how quickly we update. When alpha equals 0.1, each experience shifts our estimate by 10% of the error. When alpha equals 1, we completely replace the old estimate with the new observation. Q-learning faces a fundamental trade-off. To find the best actions, we must try different options and observe their outcomes. But once we've found something that works, should we keep experimenting or stick with what we know? This is the exploration-exploitation dilemma. Exploitation means choosing the action with the highest current Q value. Exploration means trying other actions to see if they might be better. If we always exploit, we might never discover superior strategies. If we always explore randomly, we never benefit from what we've learned. Epsilon-Greedy is a simple solution. With probability epsilon, choose a random action to explore. With probability 1 minus epsilon, choose the best known action to exploit. A typical value is epsilon equals 0.1, 90% exploitation, 10% exploration. As learning progresses, we often decay epsilon over time, exploring aggressively at first and then settling into exploitation once we've mapped the environment. Let us walk through a simple example. Consider a 3x3 grid where the agent starts in the bottom left and must reach the top right corner. Reaching the goal gives a reward of 10, while all other moves give 0 reward. We initialize all Q values to 0 and set the learning rate alpha to 0.1. The discount factor, gamma, is 0.9, meaning future rewards are worth 90% of their face value. The agent begins exploring. At first, it wanders randomly since all Q values are identical. Eventually, after many steps, it stumbles upon the goal and receives the reward of 10. This is the critical moment. The agent was in the cell just left of the goal, moved right, and received 10 points. The update rule kicks in. The old Q value was 0, the observed outcome was 10, so the new Q value becomes 1. Now something interesting happens. The Q values propagate backward from the goal. On the next episode, when the agent reaches the cell 2 steps away from the goal, it sees that the neighboring cell has a Q value of 1. Even though it receives 0 immediate reward, the discounted future value of 0.9 times 1 gets added to that cell's Q estimate. Over hundreds of episodes, this backward propagation continues, spreading value estimates throughout the entire grid. After convergence, the Q table reveals the optimal policy. The starting position has a Q value of approximately 5.9 for moving right. 2 cells later, the value has climbed to 7.3. The agent has learned the shortest path: move right twice, then up twice. At each step, it simply chooses the action with the highest Q value, and this greedy strategy produces optimal behavior. Thank you for watching. We hope this video provided a clear and intuitive explanation of Q learning. If you found this helpful, please subscribe to our channel for more content on related topics. Your support helps us create more in-depth educational material. You can also support us on Patreon, where you can suggest future video topics, ask questions directly, and receive early access to new content.